Hello there. In the last session, we discussed the three laws of motion. Now let's discuss each of them in detail. So starting with the first law, we learned that the first law introduces the concept of inertia. We saw that inertia is the property of matter to retain its state of motion. So inertia is a property to retain the state of motion. Now what exactly does state of motion mean? We saw that basically state of motion is defined by the velocity of a particle. So when we say that state of motion is retained, we basically mean that velocity is maintained. We further saw that maintaining velocity can be roughly categorized into two categories. The first is the state of rest, which is the special case where velocity is zero. And the second is uniform motion. That is, the particle moves with constant velocity. Right. So the first law tells us that matter has this property which is called inertia, and due to this property it maintains its state of motion. So what this essentially means, that if a particle is at rest, it will stay at rest, and if a particle is moving with uniform velocity, then it will continue to do so until and unless some force acts on it. Right. So let's see what this means. First of all, the most important thing here is to understand that constant velocity means that the speed as well as direction must be maintained. For example, let's consider uniform circular motion. So uniform circular motion means that a particle is moving in a circle with constant speed. So uniform circular motion would mean that a particle is going in circles without changing its speed. Now, in such a case, I want you to think about if the velocity is maintained. Let's check it for ourselves. Let's consider the particle at 2 points, point A and point B. Now, when something moves in a circle, its velocity is always tangential to its position when joined to the center. So, if we join this line to the center, you would see that the velocity is perpendicular to this line and is basically a tangent to the circle at that point. So, this arrow shows the velocity of the particle when it is at point A. Similarly, when the particle reaches point B, we can once again draw a tangent and say that this is the direction in which it will be moving. So, look at this. Do you think the direction is maintained? Clearly not, right? Because initially it was moving in this direction and now it has turned. So, if a particle moves in circle, maintaining its speed, it is still not uniform motion because the direction has changed. So the first law essentially tells us that the particle will move in a straight line maintaining its speed unless a force acts on it. Right. Now there are a lot of applications of this law. The simplest one you can see is every time when the vehicle you're in takes a turn. Let's look at that situation. So let's say this is the turn that the car is taking. So we are looking at the car from the top view and this is the person sitting inside. Right. So now as the wheels of the car turn, the car turns with in the direction of the wheels. Right. Because as you move your steering, the wheels turn and the car tends to go in the direction with which the wheels are now aligned. Right. So the car has a tendency to go from that position to, let's say, this position. Now, the person sitting inside, owing to his inertia, would have a tendency to go in a straight line and would probably have a tendency. So this is why every time a vehicle takes a turn, you feel like you're being thrown outwards. Right. A case much simpler than this is every time a vehicle accelerates or decelerates. So once again, let's consider a vehicle, and let's say this person is inside this vehicle, right? So if this vehicle accelerates, let's say in this direction, what do you think this person would feel? You know that he would feel as if he's being thrown in the opposite direction, right? If this is the forward direction and the car is moving forward, he would feel as if he's being thrown backwards, right? Similarly, if brakes were being applied, now if the car is moving in this direction and brakes are being applied, then I'm sure you can see that the direction of acceleration would be this. It would be opposite to the direction of motion. Now, in such a case, what happens? The car has a tendency to move, has a tendency to stop, but the person, because of his inertia, wants to continue to move forward. As a result, he feels like he's being thrown forward, right? And this is what happens every time brakes are applied. You are thrown forward. This is because the force that is applied causes an acceleration, and the force is proportional to acceleration. And if you remember our discussion, we had said the proportionality sign is removed using a constant which we had called mass, and we had discussed that this mass is a measure of inertia, right? So the second law is a simple expression that tells us the relation between the force applied and the acceleration that is brought about in the particle, right? So the second law tells us that force is equal to mass into acceleration. Now, force is measured in newtons. Mass, as we had discussed, is measured in kg. And acceleration, you're already aware, is measured in meter per second square. So, from here, you can also see that Newton is basically the name given to the unit kg meter per second square. This is obtained simply by multiplying the units of mass with acceleration. So 1 Newton is basically 1 kg meter per second square, right? Let's see a very simple example for this. Let's say there is a block which has a mass of 5 kg. Now, on this block of 5 kg, if you apply a force of say 10 Newton, then can you find out the acceleration of this block? It's fairly easy, right? We know that force is equal to mass into acceleration, and hence this 10 Newton force is equal to the mass, which is 5 kg, into acceleration, and hence the acceleration is 2 meter per second square. Now the first law of motion can be derived from the second law of motion. Let's see how. The second law of motion tells us that force is equal to mass into acceleration. So now, in a case where force is 0, the left hand side becomes 0. So 0 is equal to mass into acceleration. Now, since we are talking about bodies which have a mass, because only then they will possess inertia, the mass term cannot be 0, which means acceleration is 0. Now, acceleration we know is change in velocity by change in time. So if this is 0, this implies that change in velocity is 0. Now, we already know that if velocity is maintained, which is exactly what is implied by change in velocity being 0, the delta here denotes the change, the notation we have been using till now, right? So if the change in velocity is 0, this means that velocity is constant. So if the force is 0, the particle will move with a constant velocity. which means if the velocity is 0, it will remain 0, that is, it will maintain its state of rest, and if the velocity has some non-zero value, then it will move with the same velocity, the same speed and same direction. And this is exactly what the first law tells us, right? So we can derive the first law from the second law. But the importance of first law is that it identifies this property inertia that matter has, and then in the second law we basically see a way to measure this property which we call inertia. And we saw that the measure of inertia is mass. So greater the mass, greater the inertia, and greater the change to resist the state of motion, the change in state of motion, right? So these are the first two laws. Let's now look at the third law of motion. So the third law of motion said that every action has equal and opposite reaction. So we also saw what this means. This means that if body A applies some force on body B, then the body B will apply the same force on body A in the exact opposite direction. Now, this sometimes gives rise to a confusion. Let me tell you what. So let's say there is a block which is lying on ground, and let's say there is a man who is trying to push this block. So this is the man who is trying to push this block. Now, the man applies a force F on the block, and the third law tells us that the same force F is applied by the block in the opposite direction. Now, if you look at this given situation, you might think that there are two equal and opposite forces which will obviously cancel each other out. Hence, there is no net force, and hence there should be no movement, right? But this argument is wrong. The reason being that these two forces, which are equal and opposite, are not acting on the same body. So, to clarify this, we will first discuss an idea of a system. So let's talk about what a system is. So a system is a collection of particles which we are interested in observing, right? So if there is a single particle and you want to observe only this particle, then this particle alone is your system. But on the other hand, if there is a collection, then you have a choice. Your system may include only one object, or it may include both of them. Now, the importance of system is that whenever we do force analysis, you have to identify your system and then only focus on those forces which are acting on that system, right? So like in this case, there are two forces, but both of them act on different bodies. This force F, which is being applied by the man, acts on the block. This other force F, which is being offered by the block, acts on this person. So we see that the block, if you consider the block to be a system, then this block has a single force F acting on it, and hence that block can move. Same is the case with this man. If you only consider this man to be a system, then this man also has a single force F acting on it, and hence he will also move. Now, if you view both of them as part of your system, say if you include the man and the block in your system, in that case you see a zero force, and in that case you can say that there would be no movement. Now, in this case, you might feel that the man and the block, when we are viewing it collectively, it seems that the system should not move. But from your experience, you know that when you push something, it moves. The reason for that is that when this man pushes this block, he actually pushes the ground backward. So this man with his feet is trying to push the ground backward, and in return the ground applies an equal and opposite force on this man which acts in the forward direction. So it is this force that he extracts from the ground. This force which he is extracting from the ground is the force which is helping this man push this block. You can think about the situation. Say if this floor is very slippery, will this man be able to push this block? He won't, right? He would keep slipping, but the block will not move. This is because to apply any force on that block, he needs to push the ground backward. And he needs to be able to do that. And on a slippery floor, he would not get enough reaction from the ground to be able to do that. Right. So this is one common confusion about the third law of motion. Right. So we saw that to resolve this, you must clearly define your system and then list down the forces which are acting on it. So let's see an example of how we list down the forces. Right. So let's say there's a block which has multiple forces acting on it. So there's a one force of 5 Newton acting in this direction, then another 10 Newton force acting in this direction, and then let's say a 20 Newton force acting as shown. Now, when we wish to analyze the situation, we will represent this block by a point. Right. And then we will show all the forces which are acting on it. Like in this case, we have a 5 Newton force, then a 20 Newton force acting downwards, and then a 10 Newton force towards the left. Right. So what we have drawn here is called a free body diagram. Now, the reason we call it free body diagram is that in this case, we have isolated the block, represented it through a point, and then we are only showing the forces which are acting on it. We will not show any object or surface which surrounds it. For example, this might be lying on some ground or some surface, and then this 10 Newton force could actually be applied by some man who is pushing this block. So we will not show any of the surfaces or objects around which are applying those forces, but we will show all the interactions through an arrow which represents the force and apply them all on a single point. So this point represents this block, and this representation is called free body diagram. Right. So far we have learned about the 3 laws of motion. We saw that the first law tells us that in the absence of a force, the state of motion is maintained. The second law gives us the relation between force and acceleration by the equation which tells us that force is equal to mass into acceleration. And the third law tells us that for every action there is an equal and opposite reaction. So this brings us to the end of this session. In the next session, we will learn about some forces which are frequently seen. Thank you.